Mhm. You can start. Okay. Um, Hi everyone. I'm Keiichiro. I'm working with Ina Rashkari, and we did this work, monotonic multi-economic divergences, a year ago or more than that, and finally it has published today. So we're very happy. This is basically mostly about like mathematical construction and generalization of divergences or relative entropy. But since this seminar is for like everyone, theorists, experimentalists, I'll just tell you how we did generalization very um, in a simple words, and just give you the example. And then if I have time, we'll try to make a connection to physics. If you guys have any comments on physics side or mathematical side. Yeah, so this is the paper. So if you guys want to see it, you did please check this out. Okay. So let's go to my slide. Um, this. Yeah, so we have so first we will review classical case like Kubo-Ando divergences, something like that, and then we go to quantum case, which is like quantum mechanics, and we basically in our paper we made the generalization. Uh, we did the generalization even for quantum field theory, but we won't go into it. So basically, the language I'm going to use is dense images. I'm not gonna present any like modular theory and all that. But if you guys wanted to know, I can tell you about it today. And then I will show you like how uh, how it look how the multi-state Renyi divergences look like, and then we're going to go into physics. So first, this is very basic review about classical. Okay, so if you have two probability distribution on some sample space X, and then you can define this then probability distribution, which basically compares how two probability distributions are similar. So, but in addition to this definition, we actually require these two properties so that this function behaves well. What I mean by that is that if p and q are zero, then basically log is not zero in general, but we require it to be zero. And if p is non-zero but q is zero, we say it's fine to be infinite. So this is the now F divergence is just a generalization of this co-Buckler divergence. So what it is that so we have F acting on Q over P. So this is the definition of F divergence. So the F is the function from positive real number to real number with the extension to positive infinite, including positive infinity. So this is a real valued function, and this, f should be a convex function. Convex means that if you have some parameter t ranging from 0 to 1, with p1 and p2 here, it satisfies this inequality. Naively and geometrically, it looks this curve. This is a convex function. Concave function is something the other way. The maxima is above the. So this is the classical definition of F divergence. So this is I said this is a generalization of a Kubo-Ando divergence, KL divergence. So how is it generalized? Well, if you pick F to be this function, so F acting on Q over P equals to Q over P log Q over P, you get the KL divergence. So this F divergence is generalization of KL divergence, and where F is. So you can pick F to be any convex function and define some divergences. This is a classical F divergence for two for probability distributions. Now you can generalize this into Renyi divergences in classical probability case, where you have a parameter theta ranging from 0 to 1. So, so in this case, you have this function, log of sum of qx theta to the power of theta, bx of to the power of -1 theta. So this is also a generalization of one parameter generalization of KL divergence or other classical divergences. So in this case, when you bring theta to 1, then you get the KL divergence. And if you pick theta equals to half, you get something called log fidelity. So this is just log and taking a log of fidelity. We increase. You have extra log. No, that's fine. But if you take theta to be half here, you get this. Uh-huh. Yeah, yeah, I think, yeah, okay. Thanks. So, yeah, so and so we just started, okay, so this was a classical case, and we want to have some generalization, right? If you have like n probability distribution with into n parameters, like n parameters, um, we might be able to write this down. Like our guess was this, and is this correct? Then the answer is yes. So we did some generalization in quantum case, and then we found that the if you take all the states, for example, like density matrices to commute to each other, we get this classic. So this is for like n probability distribution or n states. So I'm not going to, of course, give you the proof or whatever. I'll just tell you like how to get to this idea, how to get to the construction. Okay, so far we were in the classical case where the probability distributions are commutative, like all the probability distributions commute. So we want to go to non-commutative case where we're familiar with somehow. This is the case of quantum mechanics. In quantum mechanics, we have density matrices, and then quantum relative entropy is defined in this way, which we are familiar with. And also, this is the one that Lai Mei explained to us last time. There's also another thing, quantum version of log fidelity. So this is just minus log of tracer. So these are some major information measures in quantum mechanics. And there are one parameter generalization of relative entropy. One is called Petz Rényi divergences. The other is called sandwich Rényi divergences. Both of them give you
relative entropy when bringing theta to 1. So these are the two Renyi divergences. Now the question is, like, if you have two generalization, is there any relation between them? And the answer is yes. You can further generalize one parameter divergences to two parameter divergences so that you can interpolate these divergences. And that is called originally it was called alpha z Renyi divergences, but now we're using parameter theta and r because of our we call it theta r Renyi divergences. So this is the definition of Renyi theta r Renyi divergences. In this case, theta ranges from 0 to 1 and 1 to infinity. R is the positive real. And for two density matrices psi and omega, you can write down theta r Renyi divergences in this way. So when get sandwich Renyi divergences and Pitts Renyi divergences by taking these special cases of this parameter Renyi divergences, when theta is equal to r, get sandwich Renyi divergences. When you take r equals to 1, you get Pitts Renyi divergences. And if you take theta going to 1 limit, then you get usual or usual quantum relative entropy. So this theta Renyi divergences are two parameter, two state divergences. So this was somewhat interesting. Now, the thing I want you to keep in mind at this point is that this generalization here, inside a trace or the inside the log, you see that the density matrices are placed symmetrically, which means that symmetrically in, I don't know how to say it, like you're sandwiching psi with omega with the same power here. This is kind of key to the our generalization. So with that in mind, let's study about monotonicity or data processing inequality, which is the fundamental property that we want for information measures to be correlation. So this is the thing that I may discuss last time. You have a quantum channel, which is a completely positive map and trace, completely positive and trace preserving map. So phi is a quantum channel acting on two density matrices, psi and omega. In this case, relative entropy satisfies this this inequality. So you have relative entropy of psi omega is greater than or equal to relative entropy of phi psi and phi omega. Intuitively, after you apply a quantum channel on the density matrices, these states are disturbed a lot. So as a result, two states becomes less distinguishable. So yeah, because of the disturbance. So this is the meaning of data processing inequality. In the case of yeah, size and yeah, and yes, yes. We should. Right, right. Right. Exactly. Um, yeah, so in this case, you can think of quantum channel as a thermalization process. So let's take psi to be some pure state, and omega is some thermal state. So in this case, like phi omega could be equal to omega because it's already a thermal So now you can think of you can compare phi psi and omega, and then that tells you how much psi is thermalized. Right. Right. Yes. Yes. Uh-huh. Only psi. Uh-huh. Right, but okay, but I don't. If you so on the right hand side, if you only have phi psi, but only omega, nothing on phi, this inequality might not hold. Right. Yeah. Yeah. Oh, okay. Okay. Two system. I didn't. What do you mean by two system? Yeah, 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 right, right, right. I said yes, you're right. Why did they introduce in physics alpha z physics? Yeah, yeah, yeah. But just purely like how to interpret these two pits and sandwich. So I don't think there's any physical motivation to it. Yeah. At least for the original paper, there might be like physical interpretation, but I don't know. Yeah. Yeah. So you have pits and sun. Yeah. So for pits and sandwich Rényi-divergences, monotonicity is satisfies within this region. So theta range from 1 to 2. And for the sandwich Rényi-divergences, it satisfies from half to. And there are several physical applications, interpretations for data processing inequality for sandwich Rényi and its Rényi divergences. But I didn't have time to include here. But I don't think I can say much. But there are applications. I can share you guys a paper. Anyway, so this is the plot for the region where the data processing inequality falls. So this red line is the Petz-Renyi divergences. The Petz-Renyi divergences satisfy monotonicity or data processing inequality when R equals 1. This is from here, but it's range from 0 to 2. Now, sandwich Renyi divergences is the case when theta r is equal. So if you go back to the slide here, this was the theta r Renyi divergences. To go to sandwich Renyi, you need theta equals to r. So in this plot, theta equals to r is this line. And theta, in case of sandwich Renyi divergences, theta ranges from half to infinity. And this blue region here is the place where we know that the theta r Renyi divergences satisfies monotonicity. This is okay. So this was a review for So far, we know the most generalized Renyi divergences for our yeah. Any questions? And okay, so for the generalization, so our original motivation, our original motivation is to write down these things without using trace and density matrices, because in the quantum field theory, we don't have trace and density, well-defined trace and density matrices. So we don't want to use that. And also, we want to define some multi-stage thing. So there's a nice tool called modular theory or commutative theory that we use a lot. We means like Nima's group. And so in that case, things becomes very natural, and then generalization becomes very straightforward. So yeah. So that's why we were able to do that. But here I don't use modular theory. I'll just stick to this. But the key to the one of the keys to the generalization to the multi-stage Rényi-divergences is the following. So here, if you look at the sandwich Rényi-divergences, you have this function. Like I said, omega is sandwiching psi, and you have power theta. So here in this case, you can actually write this trace into the norm of two theta. And I'll give you the definition of what this norm is. But this, so actually this trace gives you the norm. So using this type of norm, you can write down the sandwich Rényi divergences. And this is actually true for theta R Rényi divergences. So here this is the sandwich Rényi divergences that I wrote down with the norm to theta. Sorry. Yeah, this is sandwich Rényi divergences, and this norm is called L theta norm, where theta range from 0 to infinity. When theta is 2, this is the case when you this is the norm that is called Hilbert-Schmidt norm. This is the norm for for example, if you have a vector spaces, then this norm is for the L2 norm is the norm for the vectors. If you have theta to be infinite, then this is the sometimes it's called the operator norm, but the norm will give you the maximum eigenvalue of your norm. So this is called L theta, and for the norm for the operator, not just the vectors, we put your operator and theta norm. Yeah, so using this L theta norm, we have well-defined L theta norm in for any bounded operators. So in this case, because we have bounded operators in quantum field theory, we were able to use this L theta norm, and there's generalized one called L theta omega norm. I'm not gonna tell you about this. There's something well-defined norm there. Using that, we can write down sandwich Rényi divergences or theta R Rényi divergences using the norm, without relying on the trace. So using this norm, we were able to remove trace from our expression. So this is one problem. How do you define quantum field theory? Yes. Yeah. Right. So I think, naively speaking, you need to exponentiate and then make a right. How do you define? Well, how do you? Why isn't the exponential not enough? Okay. So let's say you have a Tanzania now. Okay. Well, so the finite quantum dimensional, finite quantum system. Yeah. Start with quantum mechanics. If you have a finite quantum system, let's say like qubits, um, it's just a d by d matrix algebra. So yeah, it's finite. Yeah. Right. So let's say now you take the harmonic oscillator. So in this case, it's infinite, and yeah, so it's an infinite dimensional system. So I think the bounded operators, the way you can to define is something like a coherent operator. So like exponentiate a dagger a. Yeah, minus a dagger a. Yeah, one way to make unbounded operator to bounded operator. Right, right. Yeah. So yeah, and right. So theta Rényi-divergences. So Rényi-divergences can be written by the no. Density matrices are automatically by definition bounded operator. It's called a trace cross operator, meaning that you can normalize. So this definition of density matrix is positive, and it can be normalized with trace. So, no, no. So when I say bounded operators, so density matrix is a trace. It's called trace cross operator. This is a special case of bounded operators. When I say bounded operators, it depends on which norm you want to take. So when I say bounded operators, it means that it's bounded by L infinite norm operator, not just eigenvalue and phi. Right, right. Uh-huh. Uh-huh. Right, right. Uh-huh. Uh-huh. Right, 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 right. Uh-huh. Right, right, correct. Yes. So yeah, that kind of stuff. Right, right. Conceptually, it's the same. Right? Yeah. Right. So this was just two states. So using this norm, can we generalize to let's say three states? And the answer is yes. So this is the form of it. There's something here, but let me explain what this is. But it looks like this. So in this case, you have omega, and you have psi one and psi two here. And I said three state because you have omega, psi one, psi two. And with this psi one and psi two, you have two parameters associated with psi one, psi two. And for omega, you have theta, sorry, not psi one, theta one, theta two, and you have theta zero. And these are more like probability distribution. So if you add them up, you get one. And there are other parameters. These are the gamma one, gammas. Or I think I put gamma and just put alpha. So forget about gamma here, but you have one parameter, this alpha. Yeah, you can do that. No, this is I'm just showing you that three-state divergences looks like this based on yeah. Yes. No, so that's the problem we have. We still do not have a good interpretation how to understand this because are we really comparing omega with psi 1 and psi 2, or are we comparing psi 1 and omega and psi 2? Right. So we should worry about this. We may need to make some. Yeah, so what this sharp thing. This is called Kubo-Ando geometric mean. So why do we want to use this? This is because we want to have this kind of like symmetric multiplication of positive operators. So f is operator monotone function. Oh, sorry, I forgot to define operator monotone. But this is have two operators and self-adjoint operator. Let's say a minus b. This is assumption. Then f for the operator monotone function, if it satisfies this, if it preserves the inequality that we have. This is for the operator monotone. So Kubo uh, preserves this positive structure between operators, and it tells you how to multiply positive operators to get another positive operator. So you have a bunch of density matrices, but if you just multiply density matrices with a different eigenvalue basis, you don't have that. It's not guaranteed to have one. This rho sigma is not guaranteed to be a positive. They have different eigenbases. But if you have rho r, this type of multiplication, even if the bases are like
this positive is positive definite, the same.
Sorry.
Positive it means positive definite.
Positive definite. Yeah. Positive. I think we can say positive similar.
Okay, but
Yeah.
usually people define it like positive definitely has to be symmetrical.
Positive definite is I see.
So when you multiply them, it's not symmetric anymore.
Yes, symmetric means the transpose.
Yes, or the dagger, yes, I don't know. Permission if it.
Right.
I think that rho sigma may be positive, but it's not symmetric.
Yeah, okay. Yeah, right.
But that one is clearly okay.
So this Kubo geometric mean gives you a tool to tells you how to multiply, and it will satisfy the monotonicity property, and there's something called the transfer inequality. So, so this geometric mean is very useful, and now. So this is the so we have this here. So if you have sigma rho minus r rho minus r alpha is a real number. So with this way of multiplication, if the positive operator and use.
this and take all the data and using alphas. Now I so this one is going down and this is and we don't have there's something to given a set of two states, Alice, there are Alice and Bob here. Alice prepares a state that is either row 0 or row 1. These two are the density matrices. Now she sends it to Bob. So she sends one of the state prepared. She knows which state is, and send it to Bob without telling Bob which state that is. So Bob doesn't know which state it is, but he knows that it should be either row 0 or row 1. So you need to figure out which state he got, Alice. So here the what Bob can know is a set of two states. So there's a state that he can know either is coming, and what Bob can do is apply several sets of measurements. So he can do whatever the measurement he wants, and but this measurement could involve errors. Yeah. So this is the setup of the problem. This is a quantum information problem. So is there any question for this? Destroyed. Cookie, yeah. In that case, like Bob chose a very bad measurement. Yeah. So the error is like, yeah, super bad. Like, I don't know how to say it. Error. Completely erroneous measurement. So let's work out like simple example. So given a two set of states, 0, 0, and 1, 1, it's like single qubit state, pure state that Alice can prepare. And then she sends one of the state to Bob. The possible measurement that he can do is defined by POBM. So like this is the not the measurement defined by the projections of 0, 0, 1, 1. This is more like measurement that can include some errors. So POBM stands for positive operator value to measurement. So this is like a projection, but not really. So E0, E1, they are add up to 1, but E0, E1 are positive operators. They are positive, and now the example for this POBM, one of the measurement that he can do is this. So E0 is this, E1 as this. And so Q1 is 0, Q2, when Q1 is equals to 0, Q2 equals to 1, this is the case when there is no error. Yeah, sorry. Okay. Sorry. Initially I had for E0 I had a Q1 in here. E1 I had Q2 here. But yeah, you can forget about this. Yeah, thank you. So yeah, let's forget about it. So POBM, what it tells you is that it gives you so if you calculate the expectation value of POBM for E0 with the state 0, it gives you the probability of the state in 0, 0 or 1 in this POBM. So you have state 0, 0. If you calculate the expectation value of POBM, you're getting this probability 1 minus q, and the same for 1, 1, you do 1 minus q. Yeah, so if you go back and see the definition of E0 and E1, E1 is a POBM. So if you have this matrix, yeah, sorry. So E0 you have 1 minus q, 0, 0, q minus q, 1, 1. So if you calculate this trace of 0, 0, you get the probability of getting 0. State 0, this is you're getting state. This is the correct measurement, but if you want erroneous measurement, there are two types of errors that you can define based on this. So the type 1 error is the state was 0, 0. But you misidentify it with the state 1. This is quantified by this definition. So you have state trace 0, 0, E1. So this is type 1 error. Then you can define type 2 error in the same way. State, well, the Bob got is 1, 1, but he misidentified with 0, 0. So in this case, you calculate trace of 1, 1 and E0, and you so these are the amount of errors, or like errors that Bob can get. So what Bob wants to do is that he wants to reduce these quantities, these values. So what he needs to do is the error optimization. So there are two ways to do. One is symmetric optimization, and the other is anti-symmetric optimization. So alpha and beta, these are the error probabilities. And so if you symmetric optimization, you take the average and you optimize this average. This is one thing you can do. So in our case, alpha and beta was q. So the average, this p, average error was just q. So to make to optimize the error, you need what Bob needs to do is to bring q to 0. So there's no error. When q equals to 0, what you get is here E0 becomes 0, 0, E1 becomes 1, 1. So it becomes a projection onto each state. So this is the optimized measurement that Bob should do. This is a symmetric case, but there's anti-symmetric case. And this is actually relevant to us because the relative entropy is not symmetric quantity if we swapping by swapping to this. So in this case, what you do is that you set a constraint on one of the error probability, alpha q. So you allow alpha q to be some small number. And then by fixing pips around this, you want to optimize beta. So you fix one probability error and you optimize the other type. And you can do so. This was a single shot measurement, but you can do it multiple shot. Fine by this way. The key is that the you can define. Okay, sorry, I think I swapped the role of data and alpha, but it is fine. But the important statement from model information is that you can provide upper bound for the one of the error that you're optimizing. So in this case, sorry, I think I swapped alpha and beta, but you give constraint on beta, and then you want to optimize alpha. And then to the smallest error probability you can achieve is given by something called half-Dane divergence, where it's defined by using this P alpha, which is a Petz divergence. So using the Petz divergence, you can give the optimized value for your error. You can do the same thing for, so here is the speculation, or here's the conjecture that we have, is that let's say, so Alice has n+1 states. So you have omega and psi1 to psi. So you have n+1 states, and Alice sends one of the states from the set to Bob. And now the Bob needs to figure out which state. So you do the same thing. So you put the constraint on beta, and then you optimize alpha. And again, it's upper bound is given by could be given by, which is our conjecture, could be given by our multi-state Rényi-divergences. This is like one possible connection to physics. We still don't know. Yeah, so that's yes. Thank you. Yeah. Um, yeah. So in this case, so for two states case, we know that the upper bound is given by its divergence. This is proven here. So in our case, it's a multiple state. So we don't have a Pitts divergence. That would be the first test. That could be the first test. In that case, yeah, maybe. So in this case, you can could identify theta 1 equals to theta 2, theta 3, and theta n. You can reduce it from 1 to 2 state. Maybe in that case, I see, I see. Yeah. Yeah. That's a good question. I actually don't know. Yes. And what is the relation between this? So C gives you the constraint on the other data. You're asking like what is alpha and theta? Um, you're taking theta here. Alpha is yeah, okay. Yeah, maybe you should have some alpha. No, we didn't prove it. So this is just a conjecture. So there might be a like, yeah. I don't know. Maybe this equation is not correct. Yeah, we need to. Does anyone have idea how to interpret these things? There's no question on common scheme.